Hey, let's learn a little bit. Let's talk about the reduction mechanisms. So we have two main reduction mechanisms that we concern ourselves with: the sodium borohydride and the lithium aluminum hydride, sometimes called LaH, mechanisms, and they're very similar, although they do have some differences. And so we want to talk about those two mechanisms in detail so that you understand them and what the differences are, why you might use one versus the other, that kind of stuff. And we're going to see these guys come back, so that's fun. So when we're thinking about either of these two mechanisms, I drew a lithium aluminum hydride here, and that's fine. What we do need to know is that this guy is going to be in a tetrahedral geometry, and that the aluminum is negatively charged. Now, aluminum, it's kind of like boron in that same way that we've talked about before, where it had that empty p orbital so that it could be attacked. It was a Lewis acid. A Lewis base would attack a Lewis acid, aka nucleophile attacks electrophile. And so now this guy, it's not a Lewis acid anymore, but this is our nucleophile that we're concerned with. The reason for that is the electrons are in the bond between aluminum and hydrogen, or boron and hydrogen hydrogen is more electronegative than aluminum, meaning the electrons belong to this hydrogen. So this mechanism is going to feature a lot of Lewis acid-based chemistry, and we're going to have to do a lot of thinking about what the nucleophile is and what the electrophile is. The electrophile in our case is going to be some kind of carbonyl, which this could have other things on either side, but the nucleophile will attack the electrophile, and we've already talked about, wow, that just went flying, why this is partial plus and this is partial minus, and how that matters and what that's going to look like. So let's think about those two mechanisms real quick. So sodium borohydride is not as strong as lithium aluminum hydride, and there's a couple of reasons for that. Our first reason is that boron is more electronegative than aluminum. And why that matters is if hydrogen is electronegative, it's about electronegative as carbon. If the difference between the two electronegativities of the two atoms is different, is very large, there's going to be more electron density on the hydrogen. So more electron density on the hydrogen, more electron density on the hydrogen for lithium aluminum hydride, less electron density on the hydrogen for sodium borohydride. The other has to do with the counter ion. Lithium is a much stronger counter ion than sodium, and so that's going to also play into that. And you probably don't need to know much about why for this class, but you're definitely going to need to know that this is stronger than that. Although for general carbonyl reductions, either is totally fine. You also need to know that since sodium borohydride is less strong, we can do this in a one-pot mechanism is what we call it, where we put all these things together. We put sodium borohydride in there with some kind of polar protic solvent. You could use water or methanol or ethanol. Usually we see methanol, but you could use either of those together all at once and just do the reaction all together. Lithium aluminum hydride, that's a tongue twister, I swear, is a little bit more strong, and so you can't put it all together with a polar protic solvent. You have to do this in two steps. First step, put your lithium aluminum hydride in there. Second step, add the water in HCl. It's also important, I'm going to come back to this page, to remember that for this kind of mechanism, you can have 4 carbonyls for every 1 molecule of your hydride. And the reason for that is that the reason for that is that we've got 4 nucleophilic hydrides on this guy, and once this reacts as a nucleophile, we can do something to this molecule to make it nucleophilic again. And so we're going to see that and what that ends up looking like. Okay. So the general predict the products for this is just going to come out that we're going to end up with isopropanol. Both of these we're going to end up with isopropanol. So let's start off looking at the sodium borohydride mechanism, and then we'll look at lithium aluminum hydride's mechanism. Okay. So you have your carbonyl, that's your electrophile. Our nucleophile is going to be sodium borohydride. Sometimes I like to draw it out like this, where I just show the relevant bond that I'm dealing with right now. You could certainly do that, or you could draw out the whole thing in a tetrahedral geometry or a flat geometry if you wanted to. Either way is fine. And so remember, our nucleophile is going to attack our electrophile. So our nucleophile is literally the electrons in that bond, because a hydride is a hydrogen that has the electrons. So that nucleophile is going to attack the electrophile, and we're going to kick these electrons up onto the oxygen. Ooh, whoops. So the negative charge is on that oxygen now, and now I have BH3. That guy is neutral. Remember, boron's weird. He's neutral when he has 3 bonds, 6 valence electrons. And we remember I had this in a solution with methanol. So my methanol molecules are floating around, doing their thing, enjoying life, in this solution with them. And there's a lot more, probably, a lot more methanol molecules, because that's our solvent, than there is of whatever that is, or whatever that turned into. We end up grabbing a proton from one of these readily available methanol molecules. It's truly an equilibrium. It's an acid-base reaction. So I'm going to draw one of those. You guys can go off to the side. Thank you for joining. This acid-base chemistry happens because methanol is so readily available. Also, oh gosh, he's negatively charged. Now we have methoxide, and what that ends up doing is, you remember that BH3 that was neutral? He comes in here and attacks BH3 and makes it able to react as a hydride again. Sodium counterion still exists. H, O. Wonderful. Na plus, and my boron is technically negatively charged, although the electrons still exist in this HB bond and they belong to the hydrogen. And so this reaction can happen 3 more times for the 3 additional hydrides that we have on here. Nucleophile attacks the electrophile, acid-base chemistry, and then Lewis acid-base chemistry. Bronsted-Lowry, and then Lewis acid-base chemistry. And so we can see this happening 1, 2, and 3 more times. And we're going to end up with 4 molecules of isopropanol. We're going to end up with 1 molecule of this weird borate, and we're still going to have a couple of methanol molecules living their dreams, hanging out. Anyway, that's the sodium borohydride mechanism. Let's look a little bit about the lithium aluminum hydride mechanism, because that one is certainly more complicated. So same thing, I'm just going to work with ketones, specifically acetone. Okay, I've got my hydride. Nucleophile attacks the electrophile. Remember, this guy's a lot stronger. I can't have any methanol molecules in here, or that'll ruin the lithium aluminum hydride. And so this goes to make this tetrahedral guy, just like last time. And then we end up having the aluminum with the 3 hydrogens on there. And this is a Lewis acid. This is a Lewis base, the nucleophile. The nucleophile in this case attacks the electrophile. And so I have attacked the electrophile. I'm going to return to a state where I have more hydrides to work with. And so I end up doing this reaction 3 more times. I'm going to do this 3 more times. 1, 2, 3. In this case, just like how I did over here, I'm not going to end up right away with my isopropanols. I actually end up with something that looks like this. And this is the reason that we need to have that second step with the water as our aqueous acid workup step. Because what we need to do with the water is I need to sever these bonds right here. Because my product that I care about is this organic product right there. So let's look on another page about what that would end up looking like. So I start off with my weird, oops, my bad. My weird little guy here. And so after we have completed, because we have to do this all, we have to complete our first step all the way through before we can begin our second step. So you can't just toggle back and forth between these two. I've completely finished out my first step where I end up with this molecule. Then I can move on to my water and acid. So, first step. We can just assume we have H3O plus now because water and HCl will go to make this spontaneously. Acid-base chemistry happens really fast, and we know that there's some electrons here on this oxygen that are eager to get protonated. You probably will not have to draw all of this on a quiz or exam, although you may have to, depending. Okay. So now this guy has been sufficiently protonated. He's plus charged. Weird thing about Lewis acid-base chemistry is that stuff can just break spontaneously. I don't need to make it leave with something coming out, something else coming in. I can just get that guy to leave. So now I have this keep drawing another oxygen there. That's foolish. I've got my 1 molecule of isopropanol, so I have another 3 to go. I have to do this some more. And so what am I going to do to get these other guys to leave? Well, I'm going to have to attack this with water. I'm going to have to make this negatively charged again. I have to do an acid-base transfer, proton transfer. Depending on who your professor is, they might just let you do it intramolecularly, although I don't think that that's a good choice because the intermediate would be a 4-membered ring transition state, so I don't think that that's the best choice. Honestly, it's more cumbersome, but I think the best choice is just using water to deprotonate and then reprotonate. As much as that sucks to draw out, it will be okay. So now I have H3O plus again. And another one of these guys, remember these lone pairs here, can come and grab that proton. And I'll make an intermediate that looks a lot like this, where I have an oxygen that's protonated, ready to leave. And Lewis acid base chemistry happens, he just leaves. And I have another molecule of isopropanol. So now this has to happen 2 more times, where I attack with water, I do the acid base step where I deprotonate and then reprotonate, and then I get this guy to leave. So this happens twice more. And what I'm going to end up with is 2 more molecules of my isopropanol, so 4 total. And I'm going to end up with this weird aluminum salt that's got oxygen, the OH on it, 4 times. Cool. So that was a really long, cumbersome step, but that's why we need to have 2 steps. We need to have that first step where we end up making this intermediate, and once we're fully finished making this intermediate, then we can come in with water and HCl and finish out this whole reaction. So I hope that that was clarifying. If you have any more questions, you can always comment, or we can talk about it in our Zoom recitation meetings. Cool.